potential energy diagrams. Potential energy diagrams. Okay? Now, this isn't a completely new concept. Potential energy diagrams are not a completely new thing to us because I've kind of always used our energy diagrams. Basically, you draw energy on that axis and think about the reaction kind of proceeding as the process proceeds towards products. You move to the right. And we've said, for example, when we were talking about energy, here's a chemical reaction, A plus B going to C and D. Okay? We would see, we've talked about in the past how the collective energies of A and B might be represented there. And then we could say the collective energies for C and D might be represented there. And we don't really, sometimes we know the actual values, which is helpful and nice. Sometimes we don't. But what this does is it just allows us to visualize how the process is kind of occurring relative reactants to products, right, in terms of energy. Let's see if you can remember, Jace. I know it's been, well, I mean, you weren't in 105 with us last semester, so I'm not sure if this is fresh on your mind. But if this process where A and B react to form products that are higher in energy than A and B, then what does that tell us about the change in like heat energy for this reaction in terms of a sign? Do you remember? Is it positive or negative? What do you think, Jace? Delta H for this process, positive or negative?
I would be like wrong here, but would it be negative because it like expended heat and like so it was used?
Okay, that's a good guess. Sarah, do you remember? How do we know?
I think it's positive because it required energy.
How do you know it required? How do you know it required energy?
Because I know it requires energy. Let's see, doesn't it require energy to break apart molecules?
It does.
So
it does. But energy is also released when materials come together, right?
Yeah. Right.
Who has more energy collectively? A and B or C and D?
C and D have more energy.
Yeah, that's how we know that this is a positive. Delta H is a positive, right? If we put some values on here, let's put maybe say this is 20 and say this is 10, right? And the process goes from 10 to 20, then delta H, which is change in energy, change in heat energy specifically, is always products minus reactants. Delta whatever is always products minus reactants. So 20 minus 10 would give you a positive value of plus 10, right? So that would mean that this chemical reaction is a positive value because energy was placed into the process, and that's why the products have more energy. All right? So if we look at a chemical reaction here, a different one, C going to E, for example, again, we have energy, and we have the reaction proceeding to the right here. If C is here and E is down here, then who has more energy, Camille? C or E? C has more energy. And so this process, did it release energy or gain energy, take on energy? It released energy. And so the change in, we could use overall energy in this case instead of heat energy, that's fine, would have to be what? A positive or a negative value? Positive?
Negative.
Negative? How do we know?
Sometimes I feel like it should be positive, but probably negative.
Well, we can look in.
Solid stock words for me.
Can we put values on these, pretend values, just to kind of think about them for a second? Give me a pretend value for this one, Camille. 6. That's my favorite number. Good job. What's a pretend value for this number? For this one?
It's gonna go down.
This is going to be what?
It doesn't have to be higher. It's gonna be 9.
Does it have to be higher? Yeah, because we just said it's higher in energy, right? So 9. Good. That's my favorite number. So if it goes from 9 to 6, the delta change in energy will always be products minus reactants. So what? Is it going to be a positive or a negative delta E here? Negative. That's right. Okay? So when the process loses energy, the change in energy will be a negative. When the process gains energy, and you can tell it gains energy because the products are higher in energy than the reactants, then the delta H or delta E energy change will be positive. Okay? So these are our energy diagrams. All right? And now we're going to talk about some of these energy diagrams and how they relate to the rate of a given reaction. Okay? Now let's think about this for a second. Here's a chemical reaction presented to us in cartoons. All right? Here's the chemical, N, 2 oxygens and a chlorine, and it's supposed to run into this chlorine here, collide, and react. But the products are going to be the 2 chlorines going off together and the nitrogen dioxide going off by itself. If this collision doesn't occur the right way, so as in the case of A, the chlorine hits the wrong side of the molecule, then the chlorine-chlorine bond won't form to make a product, and the collision will not result in a reaction. All right? However, if the molecules are aligned correctly and the collision occurs correctly, then the new bond will form because it's going to have a degree of stability and leave behind the rest of the other molecule, right? And a chemical reaction will occur. So this collision's occurring all the time in any sort of reactant, but not all collisions will result in products. Okay? And so an energy potential energy diagram can kind of demonstrate that for us. Let's watch this video here.
If oxygen and methane molecules are mixed together in the same container, they collide. But there is no reaction until a spark or flame is added. Why? To react, the molecules must collide with sufficient energy to break the oxygen-oxygen bonds and carbon-hydrogen bonds so new bonds can form. The additional energy needed to break existing bonds and start the reaction is called activation energy. An energy diagram can help show these energy changes. Initially, the oxygen and methane molecules collide, but do not have sufficient energy to react. A flame can supply the activation energy needed to start the reaction. At this point, bonds break and new bonds form in an exothermic reaction that releases energy. The energy released supplies the activation energy for other molecules to react, and the mixture explodes. In the air, nitrogen and
Okay. So, what this energy diagram is showing us here is that, as we did before, here's chemical reaction, A and B combining to form C, let's say. We can draw our energy diagram here and say the energy of our reactants, A and B, and the energy of our product, C. Right? This is all same as we've done before and we just reviewed. But now we can kind of connect these together with a line. And that line will represent for us what we call the activation energy. Because oftentimes reactions won't just occur because we put the material together, because they have to collide the right way, right? The right amount of energy sometimes, and also in the right way. So, and a certain amount of energy initially will exist, but for the chemical to occur, reaction to occur, sometimes you need to put in a little more energy. And then once that energy once that energy is added, the reaction occurs, and then the energy of the materials lowers down to that of the products. If it's this kind of a reaction, is this reaction exothermic or endothermic, Jace? That's right. Exo or endothermic. And it is exothermic. How can we tell, Jace? How can we tell it's losing energy?
Because C is lower than AB.
Very good.
So the product is lower than that.
And the delta energy here, the change in energy, would it be a positive or negative value, Jace? Negative value, right? Because if I took this energy, some number, let's use our favorite, 6, other number, 10, all right? 10. If it goes down, products minus reactants, it's going to end up in a negative value. Okay, so we're adding a little bit of material in between our reactants and products in this energy diagram that tells us what we call the activation energy. All right? The difference in energy from this point to this point, right, is the change in products minus reactants. All right? But from our reactants to get the process to occur, that's called our activation energy, or our EA, energy of activation. Okay. Now, chemical reactions don't always just occur in a single step. They could have multiple steps for a process to occur, right? For example, we can just choose any example here. Say 2 A's combining with a B to form a C. Maybe what happens here in this reaction, an A wandering around in its reaction mixture has to first come in contact with a B. And when that happens, A and B interact and form some new intermediate. Maybe it's I, right? Maybe for this process to occur, first A has to combine with B and form some intermediate, I. And then maybe that I needs to combine with another A. And the I will combine with another A, and maybe that will end up forming our C. So these here would be the kind of the micro steps along the way. And there doesn't just need to be one or two. It could be lots of different micro steps, right? Every single change in the actual eventual bond formation could be considered a micro step. So you might have a potential energy diagram that looks like this, where we start with our reactants, we have our products here, but these activation energies, let's see here, let's get the rest of these things on here. These, at this point here we have reactants coming together, overcoming an energy, an activation energy, and then forming some intermediate. It's not our product's over here, but that intermediate needs a little extra energy to form the product. Okay? So we can have complex energy diagrams. All right? The change in products minus reactants, that's the enthalpy of our reaction, right? Whereas, again, to overcome these activation energies, those are called activation energies, The collective activation energy for this reaction would be here, all the way to the highest energy. And that's because if we think about this as a ramp, so here's I'm drawing another energy diagram here. And if we think about this as a nice smooth ramp, and we have a bunch of pool balls, right? Billiard balls, baseballs, some sort of ball. If I give enough energy to the ball will zoom up the mountain, depending on how much energy I have given it. But it'll fall back, right, if I don't give it enough energy to overcome that. If I give it enough energy to overcome this right there, right, that means I've given it this much energy. And so it has enough energy to get up to this point. So when it falls back down here, it still has enough energy to get up to this point. So it can come back again and roll back down. So if I give it enough energy to get this high, these balls can go back and forth to this point right there, right? They won't be able to get over that, right, because I need to raise the energy even further to that point for them to get over there, and they won't be able to get over this until I raise the energy high enough for the balls to get over there. All right? But once the energy is high enough that the balls can get over, then we can begin to get some product because some of the material can fall down here. Now I'm supplying this much energy, so it's possible that these reactants may be able to come back and form the products again, right? Depending on the reversibility of the reaction. So we'll talk about that in the next chapter. But the result of this kind of a reaction, where we have multiple steps in the process, this one here, the highest one, is always what we call the rate limiting step, or the step that kind of dictates how fast the reaction occurs. Because even if I give it that much energy, I'm never going to see any products, right? I might see a lot of this, a lot of that, a lot of those. These are different intermediates, right? But I won't see any product if I haven't given it enough energy to get over my highest activation energy. Okay? So, here it is. Which one of these steps is the slowest? Step 1 or step 2? Sarah, any ideas?
I don't have any ideas. No.
Okay, all right. So, which one is going to govern the rate of the reaction? The step that, yeah, go ahead.
Step 2.
Step 2, that's right. So because step 2 is going to be the one that governs the rate, step 2 is what we call, is going to be the slowest step for the reaction. Okay? It has the greatest activation energy. Okay, very good. Now, we have an equation that can identify for us the activation energy of a reaction. All right? Using the rate law, and if we have enough information about the frequency factor, here this is A here, we can identify the rate, or sorry, the activation energy for a given reaction. All right? Here's another way of expressing this equation here. All right? We probably will not at this level have any questions about these reactions, or about these steps, these processes, or these equations. But if you did, you would just have to take this equation here, plug in our K value. A is going to be a constant, R is a constant, right? And T is our temperature in Kelvin. And we know it's in Kelvin because of the constant. And we could solve for the activation energy, or we could solve for the K. But basically what this equation does is allows us to identify either the rate law or the the rate constant or the activation energy. All right, so we are not going to do these practice problems here. So now we're going to talk about kind of what we were talking about before a little bit, the rate determining step in given elementary steps in reaction in these energy diagrams. Okay? An elementary step is kind of like these individual small steps in an overall reaction process. Okay? So here's some examples of elementary steps, elementary reactions. If A produces products, so we have some chemical, just one, and it just decomposes. The word decompose there means that this thing does it all by itself. There's nothing else to react with, no collisions. This can be called a unimolecular reaction, right? Because it's just one thing that's doing the process, or doing the reacting. When two A's or A and a different thing need to hit each other to react, then we call that a bimolecular reaction. And when you need three things to come into contact, whatever those materials are, you can call it a trimolecular interreaction. Okay? And then our rate laws, right? If the rate of the reaction is dependent on A, then we have a first order reaction. If it's dependent on A twice because A and A need to collide, then that's a second order reaction. And then you have these different rate laws that correspond to these these different possibilities. All right, so an intermediate, we talked about how an intermediate is a chemical that would form as the reaction occurs, but it never hangs around because it's quickly converted into product in the process. And a catalyst is a chemical that will interact with the reactants to help form the products, but the catalyst itself will never be consumed in the process. So when you're done with the reaction, the catalyst will always be left undestroyed or unbothered by the process. So here's a chemical reaction, and we're given the mechanism for the reaction. Now the mechanism, what does that mean, the mechanism? It means the details associated with the process. Okay? If these are the two steps, here they are, see? Hydrogen peroxide, where's my cursor? There it is. Hydrogen peroxide combining with the iodide ion to form water and this IO minus ion. That's the first step in the process. And then the second step is a second hydrogen peroxide molecule interacting with the IO minus ion to form water and oxygen, and then forming the I minus ion. Okay? So this is one chemical reaction, but it's occurring in two steps. It's occurring in two steps. Now, the steps of the chemical reaction should add up to be the overall chemical reaction. So if I take this first step here, I'm going to write it down for us. H2O2 plus the iodide ion, forming water and IO minus. And I add it to the second step, H2O2 combining with IO minus, forming water and O2 and I minus. If I add these two reactions together, I'm going to get two H2O2s on the left. I'm going to get two waters on the right. I'm going to get an oxygen on the right. These IO minuses cancel out, and these I minuses cancel out as well. So essentially what's happening in the reaction overall, if we just look at it in terms of this is what the reactants look like, this is what the products look like. We've got two H2O2s reacting and forming these things, right? However, there's more to it, right? If you don't know these little individual steps, which describe what we call, again, the mechanism, how the process occurs, right? The details of the reaction, then you wouldn't realize the importance of these different components in the process. So here, for the reaction to proceed, we need this I minus. All right. Now the I minus interacts with the oxygen to form this OI minus compound, but that OI minus compound further reacts and disappears. So you never see OI minus in the products. You see it temporarily formed, but then used up. What do we call that kind of a member in a reaction, Jace? One that's formed, but then is used up before you see it in the products. That's not the catalyst, it's the other one. What's the other one? It's an intermediate. It shows up for some reason in the reaction, and it plays a significant role, but then it's consumed also in the process, and so you never see it in the products. All right? It doesn't show up in the reactants either. It's not in the reactants to start off with. It just forms as the process proceeds, but then is consumed later on. So that's called an intermediate. Okay? But, Jace, this I minus ion, which contributes to the reaction apparently uses the I minus ion to proceed, but in the end, the I minus ion comes out, just like it was in the beginning. That is what? What do we call that? What is that one called, Jace? That's the catalyst. That's right, the catalyst. It's something that apparently helps the reaction proceed, but in the end, it's not consumed by the reaction. All right. So, what about the information regarding the rate determining step? The rate determining step. Which one of these steps is going to determine the rate? Any ideas, Sarah?
I believe it would be the first one.
How do we know?
It says it's slow.
It's
and
slow.
You said the slowest one has the greatest activation energy.
Very good.
Which is the rate determining.
Perfect. So if we were to draw an energy diagram like this and show H2O2 here, right? And it doesn't give us any information about whether this is a exothermic or an endothermic process, but I happen to know that it is an exothermic process. This is the process that drives the elephant toothpaste reaction. I don't know if you guys are seeing that. It's all over online. But anyway, exothermic process. Where would I write the products if this is an exothermic process, Camille? Where would I write the products? Higher or lower?
Lower.
Lower. That's right. So the products we said was 2 waters and some oxygen gas. All right. And then we have 2 steps, right? 2 steps. We draw 2 bumps in here. Those are our 2 steps. One is slow and one is fast. There's an intermediate, so that's the valley in between the 2 steps. Which step, the first or the second, is going to be the higher bump, Jace? Which is going to be the higher? What do you think, Sarah?
The higher bump. Let's see. Maybe the
First or the second?
first.
The first, just like you said, right? Because it's the slowest step, therefore it has the highest activation energy. Okay, very good. So, what's the rate determining step? It's the first one. Are there any intermediates? What are the intermediates in this process, Camille? Is there an intermediate? Let me see here. So here I have those same steps written that are written in this slide, written down here, right? So this is step 1, and this is step 2. What's that?
Step 1.
Well, the answer isn't necessarily a step. It's some chemical species, right?
The IO.
That's right. The IO minus is our intermediate. And which one was the catalyst, Camille?
The I minus.
I minus is the catalyst. So the intermediate
Lemma.
shows up, but disappears, so it's never in the product or the reactants. The catalyst is there in the reactants in a way, but because it's never changed, it will never be written in a reaction. You might see the catalyst written on top of an arrow like that, right? So this process is catalyzed by that. All right, very good. We learned a lot today. We learned a lot.